Hi, my name is Jacoby Melton, and welcome to my Lab 2 presentation. The purpose of this experiment was to observe the behavior of an object that's dropped from rest and investigate the effect of drag on the object. The steps of this experiment were to first record a video of an object falling from rest. I chose a crumpled up piece of paper. The second step was to use tracker software to gather data on the position of the object as it falls. Then I created two computational models of the object, one with only gravitational force considered and one that also accounted for drag force. The final step was to compare the observed data to both computational models. The results of this experiment showed that the model that accounts for drag as well as gravitational force was more accurate to the experimental results than the model that only considered gravity and the net force. The main concepts used in this experiment are Newton's second law, which describes the change in a system's motion as the result of a net force. From this we get both the position update formula and the velocity update formula, which are listed here. Also used is the gravitational force, which is the mass of the object times the gravity constant 9.8 multiplied by j hat, which is the vector in the y direction, and then negative because the object is falling. And also the equation for drag force is used, which is b, the proportionality constant, times the magnitude of velocity squared, times v hat, which is, and then negative. And the final equation used is the net force, which is just net force is equal to the sum of gravitational force and drag force. This is my tracker video for the experiment. The system was the paper ball, the surroundings were the earth and the air, and possible sources of error in the experiment where could be just inaccuracies in clicking the tracker software, and also if the object wasn't dropped from a high enough height for drag to take effect. In my computational model that only considered gravitational force, I set the initial conditions to be the mass of the ball of 0.0045 kilograms. The initial position was 0 because, as shown in the tracker video, I made the origin on the axis set to the initial position of the ball, and the initial velocity was also 0 because it was falling from rest. I repeated the while loop until the max time of 0.61 seconds, which was the length of my video. The force of gravity is 0 in both the x and z directions, and then negative mass times the gravitational constant in the y direction. I used Newton's second law for the velocity update formula and the position update formula, which are shown at the bottom of this screenshot. In the computational model that also included drag force, all of the other lines of code I showed on the screen before this were the same, and the initial conditions were the same. I changed b to be the proportionality constant. I set it to 0.001, which I found just by trial and error to find what would make the model more accurate to the experiment. And then I changed the calculation for net force within the while loop. I kept the gravity calculation the same and then added the formula for drag force. The results of this experiment showed that the computational model that included drag was more accurate to the experimental data than the one that only considered gravity, particularly towards the as time got on further. The computational model that only considered gravity got further away from the experimental and drag lines. So which models, if any, predict a terminal velocity? The model on the right is the one that includes drag force, and you can see that it starts curving as time goes on, which means that it's approaching a terminal velocity and it'll eventually flatten out. The model on the right is linear and will not predict a terminal velocity. So the one that considers drag force and gravity. What if? So in the graph on the right, I changed my computational model with drag force, and I put the initial velocity to be -5, so the object would be thrown instead of dropped from rest. And you can see that it's curved more here, and I think that it will approach a terminal velocity quicker than the other one, and it might even be the same terminal velocity because you can see that it's curving a lot more here than it is in the one on the left. Thank you for watching.